In this video, I want to show you two possible representations of the so-called Bessel function of order 0. We will call this function J0, and it will depend on two arguments. The first one is capital A, and the second one is omega. And we will start from this kind of definition here. It's an integral definition, so from minus a to a, 1 over pi e to the minus I, the imaginary unit omega x, divided by the square root of a squared minus x squared dx. Now, from this kind of definition, we will derive the series representation of the Bessel function of order 0. This is important because I will show you that we will use it when we want to derive the distribution of a sinusoid. And I want to use this kind of function here. It is possible to derive it also in another way, and which is even simpler, but I think that the derivation that we will do, not in this video but in another one, in a subsequent one, will be very interesting, and I have used this function also in my PhD dissertation, for example. Anyway, let's get to business. Let's start our derivation. In particular, now what I will do is I will simply substitute x equal to a times the cosine of t here in the integral. So this can be rewritten as integral from pi to 0 minus 1 over pi e to the minus I omega a cosine of t, and then we divide by this square root will simply become a times sine t, and then the differential of x will become minus a sine t dt, and I have put the minus sign here. Now this can be simplified like this. It is equal to integral from 0 to pi. Let's put 1 over pi here, and then I have e to the minus I omega a cosine of t dt, like this. Now what we are going to do is we are going to expand the complex exponential, so we can rewrite that by using a series representation of the complex exponential. So I can rewrite this as 1 over pi integral from 0 to pi summation over some integer q from 0 to infinity, and then here I have minus I omega a cosine t to the power q divided by q factorial dt. So let's rewrite it. We can put the series out of the integral like this, q from 0 to infinity. Then here we have minus I omega a to the power q divided by q factorial, and then here we have 1 over pi integral from 0 to pi cosine to the power q of t dt, like this. Now we are going to evaluate this integral here by making use of the formula that we derived in the previous video. In the previous video, I have derived this formula, 1 over capital T integral from 0 to capital T cosine to the power q of omega t plus phi dt. Well, this is equal to, it is the binomial coefficient q choose q over 2 times 1 over 2 to the power q if q is even, whereas it is 0 if q is odd. And remember that we defined omega as 2 pi s, some integer s, divided by capital T. And in the previous lecture, I have used k instead of q, but it's basically the same thing, right? And now what I'm going to do is I'm going to choose t equal to 2 pi, then I'm going to choose s equal to 1 and phi equal to 0. So this integral here will become 1 over 2 pi integral from 0 to 2 pi and then I have cosine to the power q of t dt. Then, of course, this will be equal to this expression here. And now let's consider the even q's, because I'm not really interested in odd q's since the result will be 0. So if q is even, you can easily understand that this integral here from 0 to 2 pi will be the same. I mean, it will be twice. Then here you have 1 over 2 pi, twice the integral from 0 to pi, because cosine of t to the power q, q is even, so cosine of t to the power q will be a non-negative quantity. Right? So I can write also this equality. This is 1 over pi, integral from 0 to pi, cosine to the power q of t dt. So I'm considering q even in this case. Now, of course, as I said, this is equal to the binomial coefficient q, choose q halves times 1 over 2 to the power q. And now we can basically substitute it here. And we have to be careful because we have to sum over even values for q. Not all the values from 0 to infinity, but only the even ones. So let me rewrite the expression here. We started from the integral from minus a to a, 1 over pi e to the minus I omega x divided by the square root of a squared minus x squared dx, and this is equal to, now we have to sum over the even q's, so let me write q even like this, and then I have minus I omega a to the power q over q factorial, and then here I have to simply substitute what we found for the integral, which is just the binomial coefficient q, choose q halves times 1 over 2 to the power q. Now we can rewrite this as q factorial divided by q halves factorial times q halves factorial, so we have q halves factorial squared, the denominator, and therefore this can be simplified. And let me rewrite it like this: summation for the even q's, and I'm going to rewrite also minus I omega a to the power q divided by 2 to the power q like this. I can rewrite it, if you think about it, like this. This is equal to minus omega a squared over 4 to the power q halves, like this, right? Because when you take the square root of this, which is this 2 here in the denominator of this exponent, you will get exactly this. So you will get minus I omega a divided by 2. So I'm going to rewrite it like this. I have minus omega a squared over 4 to the power q over 2, and then here we simply have to divide by q over 2 factorial squared, because this q factorial will cancel this q factorial here. And this is also equal to summation with q going from 0 to infinity minus omega a squared over 4 to the power q divided by q factorial squared. So we derived that this series is equal to this integral here.